Okay. Hello everyone, my name is Khanddorj Mendbayar, and today I'm gonna present our work from our laboratory, and the title is the token level evaluation and feature enhancer for transform-based model. Okay, here's today's content. I'll start by introducing my introduction and motivation, then I'll show a few good research challenges, then I'll show a few good related works, and I'll explain the proposing method and show my experiments and results. And after that, I'll conclude my presentation and tell you about our future directions. Okay, let's start with the introduction and the motivation. Okay, here's the brief history of the natural language processing. Starting in the 1950s, people started applying handwritten rules to the natural language data, and it's called symbolic natural language processing. And after that, thanks to the exponential growth of the computing power, statistical natural language processing take place. Instead of handwriting a rule, it automatically allows the machine to automatically learn the rules. And in the final stage, current best and last model is the neural network-based natural language processing, and it's learned on the end-to-end tasks, and it uses neural networks. Okay, and here's the table. On the left column, you can see the current most famous or popular challenges of natural language processing. On the right column, you can see the state-of-the-art models for these tasks. And all of these models, the state-of-the-art models, are based on the transformer model. And they are a transformer-based model. A transformer-based model is a model that adopts transformer blocks as their core and computes the high-level representation of the text using the transformer blocks. Okay, and yeah, and here are the research challenges of this. And the traditional way of increasing the accuracy of the transformer-based model is to either increase the number of the transformer blocks or the hidden state of the transformer blocks. And this leads to an exponentially growing number of parameters. And as you can see, starting in 2017, the original transformer model had 110 million parameters, but now we have 175 billion parameters model, which would take around 70 gigabytes of video memory on the GPU. Okay, and here's the problem. And okay, here are some related works that you can refer to later. And I'm going to explain about the proposing method. And yes, as I mentioned earlier, the problem is increasing the number of the transform blocks and increasing the number of the hidden states of the transform blocks. So we did not do any of that. We just added one multi-layer perceptron on top of the transformer-based model. So once the sentence is tokenized and sent through the embedding, it's processed by the transform blocks once, and then using the multi-layer perceptron, we evaluate every token in the sentence. In other words, we give a score for every token in the sentence. Then we multiply the embedding with it, and we use the transformer blocks again to compute the higher level representation of the text. And with the pooling and multi-layer perceptron, we get the final result. Okay, and here's the explanation of our proposal. And yeah, here's the comparison between the Telefe and standard transformer-based model and the standard transformer-based model. It's a tokenizer, embedding, transform blocks, pooling, and MLP. And we added only one MLP, which is very, the memory efficient. Okay, here are the experiments and the results section. And for our experiments, we have used the data set from the SEMEVAL 2020 task number 4, and the name of the data set is Common Sense Validation and Evaluation. The number of the subtask is 3, and we have only tackled the first two tasks, and there are about 10,000 rows of training in the data set. And on the right side of the presentation, you can see examples of the first two subtasks. And the first task is to which statement of the two is against the common sense. And statement one is he put turkey into the fridge, and statement two is he put an elephant into the fridge. And as we know, the statement two is against the common sense. And the second subtask is that we have given one sentence without the common sense, and there is three possible explanations are given, and we have to find the correct explanation for the statement against the common sense. And okay, to use our model and the transform-based models, we have to transform our inputs, and here's how we did it. And we used the statement one and two. We sent the statement one and two individually by the models and get an evaluation score and how much likely it is to have it against the common sense. And then we concatenate them to get our result. And for the second subtask, we combine the false statement and each option also individually, and you send it through the model one by one and get evaluation for each of them, then concatenate them and get our final result. Okay, here's the result. And as you can see, we have applied TLFA to three transform-based models: BERT, AccelNet, and Albert. And as you can see from the table, when TLFE is applied, the transformable-based model always performed better in our experiments. For example, for the BERT, it was over 20%, and for Albert, it showed the highest result of 96.4 and 94%. And here's the first subtask example. And as you can see, if the first three are the correct examples that our model did correctly, and the last three is our model missed. And as you can see, especially the third example of the missing example is that witches are made of wood and toads are made of wood. And I did not understand at this beginning, but it was something to do with Christianity, and it was obvious to the people who is Christians, and I wasn't understanding that all. And yeah, it was missing on something like this. And for the first example, inverter was able to power the continent, inverter was able to power the house. And for a person who do not know what inverter is, it's even for a person, it's hard, I think. Okay, and here's the second subtask example, and yeah, it failed on the same, the line. Yeah, and walking at the park is good for health, and it's obvious, and it did not miss it. Okay, and we to furtherly demonstrate our model's effectiveness, we have compared it with an ensemble of the Albert and AccelNet, and it which has more than double the number of the parameters, and it outperformed it. So yeah, but it's not our the humans yet, our taking the humans yet. Yeah, and here's the overall result. And yeah, to see how our proposal is affecting the transform-based model, we have done this analysis, and here's the input and output sign similarity between the
you have 1 more minute.
Okay, and in each transform-based models layers, and as you can see, the TLFE has a stabilization effect on the transform-based models. And I'm going to conclude and tell you my future directions. And to conclude, we have inspected transform-based models extensively and considered both the accuracy and the computational complexity. I proposed a method, and it can be applied to any transform-based model, and it has a stabilizing effect on the parameters in the network. And experimental results show that efficacy of our methods. Yeah, and we are hoping to explore more sophisticated methods for improving the transform-based models and implementing our proposed ideas for other proposals such as text generation and computer visions. The transform-based models are doing good in the computer vision tasks, and benchmark our proposals on general benchmark datasets such as GLUE and SQUAD. Okay, here's my presentation, and thank you very much for listening and paying attention. Thank you very much.
Okay, thank you very much, Mr. Khanddorj, for your wonderful presentation. We have one question from Ibu Ayu Purwaryanti.
Okay, I'm sorry for not writing it in the chat.
Okay, it's okay.
Yeah, your work is very interesting. You modify the layer of bird and others. So does it mean that every layer you add what is it called, TLEFE, right?
Yes,
In
yes.
each layer. So what is the background of your this one, the MLP and also activation function? Why did you choose that one?
I will. I was interested in natural language processing, and I looked through the state-of-the-art models for each of the tasks, and all of them were based on one model. So I thought I should, if I can improve a base model of that, I can improve every task of the natural language processing. And it may be a little ambitious, but yeah, and that's how I
Yeah,
got into this
why,
idea.
did you choose the MLP and then add with this activation function? Why don't you choose other kind of topology?
Okay.
What is the
Uh,
basic
uh-huh.
idea?
In the recurrent neural networks, there is attention mechanism, and it weighted every tokens, and it showed better results. Uh, to give weight to the tokens, the RNN had the similar approach for the recurrent neural networks, and yeah, it was inspired that. Did I answer your question?
I mean, why don't you choose other than not the MLP? Have you tried other than the MLP to add
No, I
for the
have
transfer
only
function?
tried the MLP, but I have
Oh,
tried other activation functions, and yeah,
okay. And the best activation function is
activation function is 1 plus sigmoid, and the
okay.
1 plus sigmoid x, yeah.
Why?
Because its output range is between 1 and 2, and it does not distort the already trained parameters of the transform-based model, while it also, have the ability to change something. Yeah.
Okay, thank you. I think it's interesting if you add you try another thing, not only the MLP, and then try to compare.
Okay.
Thank you very much.
Thank you very much.